it's my pleasure to introduce Professor Aparna Baskaran from Brandeis, and she's going to give her first lecture today about foundations of non-equilibrium statistical mechanics. Thank you very much.
Does this work? Yes. Okay. All right. Let's get started. It's my first time south of the equator, so I'm still timid and nervous seeing all of you guys over here. So let's get started with the big picture context, just to make me happy for a few minutes before I start into a lot of math and make all of you unhappy. Now, the outline and scope of what we are going to do in today's hour and a half that we have together is I'll start with some philosophical framing of active matter, what we are learning in the school, what's happening out in the world kind of thing. Then I want to reflect for a moment on learning, how best to use your time when you have agreed to sit here for an hour and a half and listen to another person talk at you, right? And then we'll launch into the actual physics that I want to talk about, which is Brownian motion, fluctuation, dissipation, and diffusion equation, and things like that. Okay. So let's start with philosophizing. What is the game? We are humans. We're doing something. What are we doing? So let's take this present moment. I'm standing here speaking with you, and you are listening. I could narrate the present moment in a number of different ways. I could narrate it in the first person by asking questions like, what is hearing? Is there only hearing, or is there a hearer in addition to hearing, and things like that? This would be the game that meditators and mystics would play, and it's outside the scope of science, so we won't talk about that. Then there's the second person story. The second person story of the current moment would be, oh, there's a woman in her 40s, probably Indian, standing, talking to me, and I'm already bored. Some English description of what's happening right now. And then there's a third person description of what's happening right now, which is that there is activation of my vocal cords that's setting up particular vibrations that are then carried by the air in this room as transverse waves to your inner ear. Your inner ear has hair cells that respond to the mechanical perturbation. And when the mechanical response of the hair cell is converted into an electrical signal that shows up in your brain, and based on whether you know English or whether you like what the words coming out of my mouth are, various feelings and thoughts and stuff are emerging in your brain. Okay? The difference between the second person and the third person story is the third person story is all math. Every step of the way, if I wanted to talk about a membrane vibrating, I mathematize it. If I think about air waves transmitted across the room in the medium, I mathematize it. And if I want to understand how my ear cell works, I mathematize it, right? And all of this math is StatMech. There is no observed phenomena without StatMech. High energy theorists may disagree with us, but they are also wrong. Whenever they have to measure something, they have to use StatMech, okay? So there's only StatMech. And so what we're going to do is we're going to talk about StatMech today. And I want to focus on the third person aspect, namely that if I talk about physics without talking about the math, I'm telling you a story, okay? That cannot be the purpose of this classroom. So we will take the bull by the horns and do a bunch of math, okay? Now, the utility of doing things mathematically, when you observe a phenomenon and you mathematize it, you've identified the right concepts and you have found the mathematical relationship between those concepts. Once you get there from natural phenomena, you can build it, right? If I have an idea that I need a vibrating membrane that converts mechanical energy into electrical energy, that's all I need to be able to build a speaker or a microphone or anything else like that. Mathematizing allows us to translate beyond whatever context that we are thinking about in a particular situation, okay? So that's the value of trying to do it this way. Now, a little bit more philosophizing. This is for anybody undertaking any intellectual endeavor, the third person story. But what are we doing? So I thought what we were doing was we were thinking about what is the definition of life. So I asked Google. And Google told me things like this: the period from birth to death of a living organism. Apparently, life has the units of time and can only be determined after the organism dies. That is useless. Then it says something like quality that distinguishes matter that has biological processes. Like, I don't even understand the English words here. What, pray tell, is a biological process? I don't know what to do with that either. A slightly better definition is a self-sustaining chemical system capable of evolution. This set of English words, when mathematized, is the route taken by synthetic biologists and gene network theorists to try to understand how life functions emerge from complex chemical reactions. Okay? This is a very, very interesting and evolving field of knowledge at the present time, but I don't know anything about it. So I can't actually use this definition to frame what I'm talking about. So a better definition that works when I wake up in the morning and don't want to get out of bed and I have to motivate myself to get out of bed, I say, oh, I will understand the definition of life. Definition of life is homeostasis, organization, metabolism, growth, adaptation, response to stimuli, and reproduction. I have a laundry list, right? And I can spend the rest of my life sorting through this laundry list and I can be happy, which is the game that we're playing right now. In this school, in terms of the content that Julia and Rodrigo and Francesco and I will talk about, we'll mostly talk about organization with a little bit of stimulus response in there, right? Everything else we will ignore in what we're talking about. So the game is to understand how life comes out of matter. Now, of course, active matter got started by physicists looking at movies such as this and saying, oh, I know what's happening here. These guys are flying spins, right? There is order, there's a spontaneously broken symmetry direction. Let's build a Ising model on speed, and we can have active matter. That's where we got started, but active matter has come to encompass many diverse systems. Many people in this room have thought about systems such as streaming in a cytoplasmic cell, the crawling motility of a cell, collective behavior in bacteria, collective behavior in vibrofluidized granular systems, and so on and so forth. And what unifies all of these things under one umbrella of active matter for us people is that this is a material made out of microscopic engines. They're coupled to each other through local interactions and are collectively able to do work on a much longer length scale than the engine itself, right? That's the umbrella under which all of these systems come in from the perspective of statistical mechanics. Okay. Now, let's drill down and talk about what will we be doing in this course, that is to say the 4 lectures. You and I have embarked on a 4-lecture relationship. You have granted me 9 hours of your life. So I'm now telling you what I plan to do with your 9 hours. I want to stick to the simplest engine, that is 6 hours, I multiply, thank you. I can't do arithmetic even in private, definitely not in public when I'm on display, so that's reasonable, thank you. So the simplest engine that I can imagine is something where there are some magical inner parts that I don't care about, but the only thing that shows up in the rest of the world is a velocity, that object moves, right? So we'll stay within the self-propelled particle picture of an active matter. And I will mostly be talking about one self-propelled particle. Interactions, fanciness, leave to those guys. We will mostly be talking about one self-propelled particle. And it's not even a little bit boring. Okay? So you can decide whether you agree with me or not at the end of tomorrow's lecture. Don't decide today. For many self-propelled particles, what I'll be talking about are ideal gas properties. I will still try to keep the self-propelled particles non-interacting and talk about ideal gas properties. But I can't get everything I want out of just the ideal gas. I have to turn on a little bit of interactions. So I have to talk about MIPS a little bit. But I'm assuming that Rodrigo would have already set the stage for us to be able to do everything MIPS. So I can just borrow it and go and do what I want to do with my ideal gas. Okay. So those are the things I'll talk about in the first 3 lectures. The 4th lecture will be active matter in general. I will take this making life out of matter seriously, and I'll talk about all of the different experiments that have been done, what are the theoretical considerations that have been considered, and particular challenges that we are facing right now, and how we are trying to understand that. So that's the big picture scope of what these 4 lectures would contain. But today, there's no active nothing. There's just plain matter. There's no life here. We're just going to take just plain matter and try to understand the math that we will be using when we get to active matter, okay? And the reason that you want to start with just plain matter is the stories we told about heat are similar to the stories we tell about life right now. Life seems magical to us now. Heat felt magical to us before we figured out non-equilibrium stat mech, right? So you want to start with heat and then ask, okay, how are heat and life different? That's how you want to go at this problem. So I'll start with just plain matter. And that's all by way of introduction in terms of what we will be doing over the next 4 lectures and so on. Now, let's take a couple of minutes and reflect on learning inside the classroom. Usually, I have a 30-lecture relationship with my students. So I spend 15 minutes talking about how you should learn in the classroom. You guys are going to get the lightning speed version of it because I don't have to love you after 4 lectures, right? So I don't care. But for the 4 lectures, the guidance that I want to offer is the following. We spent crap loads of fuel and crap loads of resources to be in one room. So what advantage do you have in being in one room versus watching this on YouTube while lying in bed? The advantage you have is the possibility of conversation. I make sounds, you have to make sounds back. The interaction of those 2 sounds will what will result in meaning eventually. Does that make sense? If you just look unhappy, that doesn't help me at all. You might be unhappy because your girlfriend broke up with you last night. How will I know? You have to open your mouth and say something. Externalize your unhappiness. Then we can try to see if we can go somewhere, right? That's the first piece of guidance. The second piece of guidance is just associated with us as humans. There is only one, there is one reason to talk. There are 2 reasons to talk, 3 reasons to talk. I don't know. I'm losing track of the argument. But basically, when you want to speak up in class, just go ahead and speak up. If 3 or 4 people speak up at the same time, that's okay. We can just sort it out after we hear the voices, right? Just speak up. Be spontaneous. Leave your mouth free. That will help you ask your questions as they arise. And don't hold back on account of other people will think I'm stupid. Everybody always thinks you're stupid, but they have no time to think about you. They are busy thinking about how everybody else is thinking they are stupid. So don't worry. It is a measure 0 process in somebody else's head. That's totally not worth worrying about. Okay? So in terms of practical guidance for this thing, I would suggest that you should write notes. One moment. This is a nervous stick. I feel like my hair is falling apart whenever I am nervous. When I'm not nervous, I don't notice it for hours, so I'm sure it's not my hair. But, okay, so write notes, even if it is to just throw it away. The purpose of writing notes is just to engage with your own thoughts while the lecture is happening. So write notes even if you're going to just throw it away. Ask questions. As I mentioned, conversation is critical. And pull together, work with your peers. There will be various in-class exercises that will show up as these lectures progress. And I will ask you to work with your neighbor or work with the person behind you or something like that. That helps. That helps in terms of regulating your own explorations in some dark alley that I push you into. Does that make sense? So those are the guidance. Now let's get started with what we're actually doing. So I want to talk about non-equilibrium statistical mechanics, and I want to begin with the standard Gadankan experiment that we would start with. I am in a classical world. I am a theorist, so I am allowed to turn off gravity. I put 2 balls inside a box with different velocities in one corner of the box, and I make a movie of the resulting dynamics. And I assume that everybody in this room will agree with me that I could show the movie in reverse to somebody else and they cannot tell that I'm showing the movie in reverse, right? Absence of gravity, 2 balls in a box, classical mechanics. It is time reversal invariant. There is no way with the post-processed movie that I can tell that you are showing it to me backwards. You could lie to me quite effectively, right? But if I change it to 10 to the 23 balls, and repeat the same experiment, start the 10 to the 23 particles in one corner of my box and let it go, you can always tell that I'm lying when I show you the movie in reverse, right? And the mathematical description that I would use when I have 2 balls in a box would be classical mechanics. I would need a Hamiltonian and initial conditions. I will need dynamical equations that are explicitly time reversal invariant, namely the Hamilton's equations. And if you give me the initial conditions for every ball in the problem, then I'm done. I just have to plug the initial conditions into the solution of my differential equation, and I know everything there is to know about the system. Non-equilibrium statistical mechanics is the bridge. It's the mathematical language that allows me to build a bridge between the case where I have microscopic reversibility to the case where I have observed irreversibility. Okay? There are many ways to build this bridge. So I could start from Newton's equations, walk my way through the BBGKY hierarchy, build out a kinetic theory. All of these are systematic ways of coarse graining my system so that I change from the clock and ruler I need to measure individual molecule collisions all the way out to the clock and ruler I actually have, right? We will not be doing this because I have one lecture in which to give you some foundational overview, so I will not be talking about this particular thing. There's another body of work which is also very elegant language that allows me to build all of non-equilibrium StatMech from scratch, which is the stochastic thermodynamics approach, where I start with heat and work. I define them microscopically. Microscopically, heat is kinetic energy, work is potential energy. Only macroscopically are heat and work two different things, right? So you start with your microscopic definition of heat and work, which will be kinetic energy and potential energy, coarse grain systematically to get to heat and work at the macroscopic level, where heat and work will no longer be the same thing. That would be stochastic thermodynamics. We'll talk a little bit about stochastic thermodynamics a little later in this course. But what we will actually be doing is we'll be doing diffusion. I'll be talking about Fokker-Planck equations and Langevin equations. The reason to choose this problem is the math is very easy. Everything can be explicitly done. And conceptually, nothing different is happening in any of those other fancy schemes. They are just mathematically more messy. Apart from that, conceptually, it's exactly the same story. So we'll spend our time talking about the diffusion, Fokker-Planck, Langevin equations and stuff. Okay? So that's the framing. Now let's talk about non-equilibrium statistical mechanics of a Brownian particle. The phenomenology I'm starting with is diffusion. If I take a glass of water and I put a drop of ink in it, it's going to spread. And the other piece of phenomenology that I'm starting with is damping, namely that if I pull a particle through a fluid, if I exert a force on a particle moving in a fluid, the particle gets a velocity and not an acceleration. So when a particle moves inside a fluid, I am somehow in a world where Aristotle is right. While if the particle was out in air, I have to use Newton. Right? A force does not always result in acceleration when the particle is moving through a fluid, and in steady state, it basically results in a velocity. Right? So that's damping. These are the two phenomena that I want to focus on. Both are signatures of irreversibility in macroscopic systems, because both of these phenomena are not time reversal invariant. If I had Newton's equations, they would be time reversal invariant. If I have some Aristotelian equation where a force is equal to velocity, that's not time reversal invariant. Right? So both are signatures of irreversibility. And both are dynamical phenomena. Even though when we were babies, we used to pretend that these things are things that we can understand from some kind of energetic arguments and stuff like that, you actually can't. You have to do dynamics to really get at it. And both arise due to fluctuations of the water molecules. This you guys know. The reason I get diffusion of a particle in a fluid is because of the collisions with the molecules of the fluid that I'm not seeing. If I could see the collisions of all of the molecules in the fluid, then there's nothing random about the motion of the particle. Right? So diffusion is a process that comes about because of random kicks that come from the environment. Damping also comes from exactly the same phenomenon. Because all that's happening is I'm moving in this direction, there are more particles colliding with me this way than that way, and so they end up absorbing more of the momentum that the force is putting into me, and it ends up being a constant speed motion rather than an accelerating motion. So both of these are arising through the fluctuations of the water molecules. And they are simply related to each other near equilibrium. I am assuming that everybody has seen this version of the fluctuation-dissipation relationship, which is the Einstein relationship, that the diffusion coefficient is temperature divided by the friction. Yes? For a moment, can I ask you to close your eyes? Can you raise your hand if you've seen this version of fluctuation dissipation before? Close your eyes. This is not for peer shaming. This is for my knowledge. Yes, thank you. All right. This thing is called the fluctuation dissipation theorem. And what's going to happen over the next 15 minutes or 20 minutes or so is we're going to try to get to this fluctuation dissipation theorem some other way. Okay. I want to begin by considering a 1 micron sized particle in some Newtonian fluid, let's say water. And I write down the equations of motion for the one particle that I put inside the fluid. These would be the Newton's equations that I would write down for one particle in a fluid, right? I have just dp by dt is equal to f. And the force is usually assumed to be a frictional force, a linear frictional force. That is to say, the friction coefficient is independent of velocity. So the faster the particle moves, the more the drag force on it, but the p-factor does not change with the velocity. Okay? So this linear friction force is a common approximation that we use when studying particles in fluids. And the friction, you have to do some low Reynolds number hydrodynamics to figure out the friction. You take the fluid as a continuous medium, put a no-slip boundary condition on your colloidal particle to figure out what the friction is. This calculation nobody does anymore. This was very fashionable in the 19th century, so you go find it in a book, right? And for a sphere, it is 6 pi a eta. So what I have for my Newton's equations for the story I just told you is mdv by dt is minus friction constant times velocity, which means that the velocity as a function of time decays. And if I wait long enough, the velocity is just going to be 0. Is this okay? I'm assuming that everybody knows how to solve a first-order linear differential equation. And if you don't worry. I'm going to push you down the deep end of the pool and make you do it. Okay. Now, what is the temperature of this particle based on the story I just told you? I think this is a stupid question because that's a reasonable answer. And I'm shameless. I'm going to wait here till somebody says something. Kinetic energy. Okay, the velocity, I agree with the assessment that we got that the temperature should be the kinetic energy, but the kinetic energy of my particle is 0 in the story I just told you because it comes to rest, right? So this is a stupid model because I know that my particle should be at the temperature of the fluid, right? What am I missing? I assume everybody knows what I'm missing. By taking only friction into account, I have only accounted for there are more collisions on this side than on the other side. But there is all kinds of collisions from all other directions that I'm not accounting for in the story I just told you. And that's what I'm missing. That's why I'm getting an incorrect temperature for my Brownian particle. So I fix that by adding a stochastic force. So this guy is called the Langevin equation, and the eta is a stochastic process. Now, what I'm going to do is I'm going to switch from the slides to the blackboard to talk about stochastic processes, okay? To truly get familiar with the math of stochastic processes, we need 3 or 4 lectures. I'm going to cheat and give you a big picture sense of what one means by a stochastic process. So what I want is I want a process eta. What do I mean by process? I mean that eta is some function of time, and the time runs from whenever I started my experiment to however long I can do my experiment. Is that okay? We are in, thank you. We are in the practical world. Time does not go to minus infinity or plus infinity. It starts when the experiment starts and stops when the graduate student gets bored. So it runs from 0 to t. And I want some function eta of t. So I want to begin with, talk in a discrete language. So let me discretize this time interval into 0, t1, t2, tn minus 1, and t. So I just discretize my time using some delta t, and let's say there are n bins in my discretized time. So what I have is I have eta naught, eta at time 1, and so on, eta at time n minus 1, and eta at time n. Right? So my stochastic process now is a string of numbers. Is that okay? Now what you do is you choose this number at each time step randomly. Okay? So at each time step, I sample eta from a probability distribution. I say that the probability of eta is e to the minus eta square by, I don't know, 2 kbt, let's say. And with an appropriate normalization that I cannot remember right now. I could barely compute 1.5 times 4. I'm not going to do Gaussian integral and screw up the pi. So I draw from this random distribution an eta, and I put it here. Then I go to the next time step. I again draw from this random distribution eta and put it here. Okay? So what this says is that eta at each time obeys a Gaussian distribution. If I just looked at eta at time 0 over many, many different trials, I would get a Gaussian distribution, right? And eta at subsequent times are uncorrelated. They are independent Gaussian random variables, right? So this set of numbers are independent Gaussian random variables. Right? So if I take eta at any given time, it will have this distribution. And therefore, eta at any given time, let's call it time little n, this square is going to be 2kbt. And eta at any average is going to be 0. Yes? Okay. Now, so this tells me how to construct my random variable at each time step. What do I mean by this trajectory eta? I mean that for every time I do this experiment, I generate a new set of n random variables from which to compute my trajectory. Okay? So when you think of eta as a function of time, this eta as a function of time is actually n random variables. It's a sum of all of these guys, right? And I assume you guys know that if I take a sum of many different random variables that are all Gaussian, I can write a joint probability distribution for all of them. Yes? So for example, if I had a random variable x that was Gaussian distributed and y that was Gaussian distributed, then p of xy would be e to the minus x square plus y square by whatever their width is. Yes? The joint probability distribution will just be the product of the probability distributions because these are independent processes. So when I do this for this guy, people usually write it as the probability distribution for eta. I don't know what notation I want to use, 0 to t maybe, is e to the minus integral 0 to t eta of t dt prime 1 over 2kbt. Eta square. That's the continuous time analog of this guy. So this probability distribution is not a function of eta, but a functional of eta, because it depends on all of the etas. And when anybody says, let's calculate the noise average of some quantity, what they are saying is let's integrate over all possible paths eta, let's compute x on each of these paths, and average it with this probability distribution. This is where the path integral formulation of stochastic calculus comes from. This is a very powerful technique that you can use to solve lots of problems once you get familiar with functional calculus. So this is what I mean by a stochastic process. But what we are usually told when we are reading a paper or listening to people is that this noise has the property that its average is 0 and its 2-time correlation function is delta of t minus t prime with some number here for the strength of the noise, right? Isn't that how we normally talk about Gaussian white noise? But you want to be able to break down the Gaussian white noise into either a path integral or a discrete representation like this to be able to do the calculations that you'd want to do with the noise. Okay. Questions or comments about what has transpired up to this point? No? Okay. Now, what did we do so far? I just talked about these two equations. Is that okay? In the following, the noise strength will be called B, because I don't want to call it a temperature just yet. I want to let it be whatever it is. Yes? It says cumulant. I'm sorry, I did not tell you that. It's a cumulant. So a cumulant and a mean are two different things, right? You guys know that the first cumulant is the mean. The second cumulant is the standard deviation. The third cumulant, I don't know if I can write it without making a mistake. It's called skewness. And the fourth cumulant is called the kurtosis. Cumulants are basically means, but with the means subtracted out. I want to take moments, but I want to subtract out the mean from my calculation of the moments. There's a systematic way to do it. And whenever people report properties of noises, they mean the cumulant. They don't necessarily mean, because I could have a process that has some drift-like thing over here and still have a Gaussian process for the quadratic. So there exist such processes for Levy-Frey problems and things like that. So this is, C is cumulant, sorry. Other questions or comments? Okay, let's move on. Now, if I just take the equation on the top of the slide and integrate it over time, this would be the equation I would get. Yes, no, maybe? I don't know how the second term came about. If there are no takers, I'm going to assume this is all working. Okay, I'm going to assume this is all working. Now, unlike Julia, I'm not kind. I won't assign work and then give you any choice. Now, you have to do the following, and I'm going to come snoop to make sure that you're doing the following. Compute the variance of this speed. What I want you to compute is v square of t from the equation that is there on the board. Then compute the noise average v square of t. And what I suggest you do is share your pain with a neighbor. Yes. What was the suggestion? No, I'm suggesting that take this expression for v that's on the board, v of t, write down v square of t first. Then compute the noise average. First, just take that expression and whole square it. Expand out the whole square, write a square plus b square plus 2ab, then do the noise average. And to be able to do the noise average, you only need these two pieces of information. There has to be head bent over something and there must be some scratching. That's what counts as writing. At least you have to pretend, right? Keep your neighbors honest by peeking at their notebook. If you're watching me do this, it'll be like trying to learn a bicycle by watching a YouTube video without ever touching a bike. All physics lectures are like this. We stand here, we show you YouTube videos of bikes and talk about how beautiful it is to ride a bike. We never hand you a bike. Unless you do the math, there is no bike. Okay, everybody look up for a moment. There is an expression for V square on the board. Is that what you got? Everybody okay with my expression for V square? Yes, ma'am. 2 times, yes, yes, thank you. Other typos? Where should the M square be? Anywhere else? What did I do? V0 square, yes. What else? Is it correct? Okay. Let's assume this is correct. Now I can compute noise average. This doesn't depend on noise, so this is 0. This has 1 noise on it, so this is 0. This has 2 noises, so this gives me 2b delta of t minus t prime. Is that correct? If it went by too quickly, now is the time to yell at me. Because if you let me get away with it, I'm going to get away with a lot more. Yes. Oh, there is no noise here, so I can just keep it. I don't care. So maybe I should just keep it. Shouldn't make it 0. It just depends on initial condition. There's no noise here, so I don't really care about it. And it's going to go to 0 when I make time long enough, so I just throw it away. But you're right. There is no reason to throw it out yet. Good. What else? Did the noise averaging happen too quickly? Okay, let's look at what I'm doing. I want to put this angular bracket around this guy, right? This angular bracket is a quantity defined on eta. So wherever I see eta is where the angular bracket has to sit, because that's the only thing that depends on eta. All of this stuff doesn't depend on eta. So the angular bracket shows up here. This is where I have to do the integral. Similarly, if I look at this expression, only etas are here. All of these are just time and mass and things like that. So the angular bracket shows up here. I have an angular bracket of 1 eta, and I have an angular bracket of 2 etas. I go here and look at my cheat sheet. Angular bracket of 1 eta is 0. Angular bracket of 2 etas is 2b delta of t minus t prime. I just plug it in here. Yes? Now, once I get to this point, the rest is easy. I use one of these integrals to get rid of this delta function, and then it's a bunch of exponentials which I can integrate. Nobody can integrate these days, so you ask Wolfram alpha. So that's fine. Integration is not a skill anybody needs anymore. So if I compute the variance, I would get an expression that looks like this. There's a typo in this expression. It also has the square missing on the v. But otherwise, I think it's okay. I have some part of the mean square displacement that depends on the initial condition, but I don't really care about the initial condition, because if I take the long time limit of this expression, the initial condition is going to drop out, and I'm just going to get b over zeta m. Yes? Okay, let's assume that's okay. If I take the time going to infinity of this expression, it had better correspond to the equilibrium temperature of the fluid. I mean, we did all of this circus because when we started with only the damping, I got a different temperature for the particle than I would have gotten for the fluid. Now, I have to make sure that the particle temperature is the same as the fluid temperature. The particle temperature, as we heard earlier, comes from its kinetic energy. So you have to calculate the RMS of the velocity to find the temperature. So it has to be kBT by m. That implies that this guy B that I didn't want to name before has to be equal to zeta kBT. For this asymptotic property that I expect the system to have. I expect that if I leave the particle alone in the fluid long enough, the particle temperature will be the same as the fluid temperature. And that tells me what I can choose for the noise. Basically, what we are doing here is we artificially partitioned the effect of the water molecules into friction and noise. But the partitioning was artificial. They were both coming from water at temperature T. So you go back and you put the self-consistent condition saying that at T goes to infinity, this thing has to better go to equilibrium. That self-consistency asymptotic condition saying that it has to go to equilibrium is what gives you fluctuation dissipation. And this is what we don't have in active matter. There is no asymptotic condition that I can enforce on that system because the system is going to do what it wants to do. It has its own energy. It doesn't have to equilibrate to the temperature of my environment. So this self-consistency condition is what we will lose when we go to active matter, but everything else will carry over. Okay. That's all about the Langevin equation for a moment. Let's talk about diffusion. I assume that this is the form in which you think about diffusion. That if you look at the RMS displacement of some particle, it grows linearly with time. If you look at x square of some particle, it grows linearly with time. Is this how you think about diffusion? Is this how you think about random walks? No, I do not. I think about random walks some other way. What can I write on the board that will immediately say random walk, Brownian motion, diffusion, all those words to you? No? Okay. Let's assume this is how you think about diffusion as well. Now, how do I get this from all of the stuff that I already did? I just have to repeat the calculation for the position. I was so far solving the equation for the velocity, right? Now, I take the solution for the velocity, put it inside my position equation, and integrate that. Okay. So let's integrate that and make sure that I take displacement from the initial coordinate, whole square it, compute the integral, and I'll get something at the end of the day. I'm not going to make you do this because you're going to do it anyway. But for the moment, you get some answer that looks like this, where you have some expression that if you look at it, at long times has the correct behavior, the diffusive behavior, right? But at short times, there's a whole bunch of other crap that can be there, right? It just turns out that when you are working with the simple system that we were working with, usually when we have to wait long enough for it to become diffusive, all of these time scales become unimportant. When these time scales remain important, as they do under some circumstances when you're dealing with active matter problems, you have to go back to scratch and ask, what did I throw out when I assumed the thing was diffusive? And put it back into the problem. The classical diffusion problem, the one that we just solved, is a treasure trove of mathematical secrets that people forget when they tell the English story. So it's worth going back to these basics that will help us do new things. Okay. Now let's pause for a moment and do an in-class exercise. For this part, I'd like you to form groups of 3 or 4 people and think about this question. Write down the answer. One of you can act as the scribe, and I will ask you for what your answer was. If you're sitting alone in some corner, find a friend or find an enemy. They don't have to be friends to do these exercises together. Could you pass a few of these down? Here. Oh, sorry. Just hand a few down. Can you hand them down a few? And pass these in the back too. Just hand them around. I don't know how many I'm handing. I'm just randomly handing a few. We'll wait for the diffusion process to stabilize. And there should be some random motion in the room, right, to form groups. It's only the paper that's diffusing. The center of masses are not moving. Okay, now I'll give you 5 minutes to think and discuss about the questions on that piece of paper. And then I will call on you guys to tell me what you came up with, in case you were curious. I'm not expecting you to answer the question. Did everybody get a sheet of paper? Okay, here. Anybody else? Is there a traffic jam somewhere? Here, Julia. Be as concrete and explicit as possible. What you've been handed is a movie. Do you guys understand what I'm asking? Wait, let me turn this on. Yes. Are working in groups, I recommend that one of you act as scribe and write down your conclusions so that you can just hand them to me. I told you I'll be policing you. I have to force feed you this stuff. No, this is for the next part. Yes. Oh, I'm not going to let you. All right. Now stop being nice to each other for a couple of minutes. Tell me, what should I tell you? I can't just hand you the movie as a data, right? What should I tell you? Yes, sir. Frame rate, okay? That frame rate will tell me what time means. Okay? What else? Resolution of the microscope. Why do I need to tell you the resolution of the microscope? Okay? So this is going to tell me if I'm in seconds or microseconds or what. This is going to tell me if I secretly gave you data from a telescope. Because how will you know? I could have given you data from a telescope. The data from the telescope looks the same as the data from the microscope. Okay, so I can find out meters or parsecs or whatever on my data. What else? This is just visual data. All visual data is the same. Everybody's playing the same game. What else? Temperature, okay? All right? Viscosity. What else? There was a hand up here somewhere before I turned. The mass. Mass of what? I made a movie. How would I know anything about the mass? How? Okay. Fine, fine. I will build a careful micron-scaled weighing machine and figure out the mass. Fine. I really don't want to do that, but I will. Okay. Yeah, okay, I know that. He wants to know if it has some electrical properties that needs to be worried about. Okay? Let's assume that ENM is irrelevant for the moment. Okay? Because if we go down that route, there's a whole laundry list of things you need to know. Now, I gave you a movie. I want you to tell me something about the properties of the motion you're observing. You didn't need to know any of this crap to know that.
Propulsion, if they have self-propulsion.
You figure it out from the data.
Okay,
how will I know? My E. coli might be dead. So yes, tell me what else. That you count. I gave you a movie. I pipetted a little amount of something into a cup. How will I know how many particles I put there? You count. Yes. Randomly distributed. You want to know the initial conditions. Is that what you're asking? Or you're saying I should give you more than one movie? Articulate for me. What does it mean randomly distributed? The particles should be everywhere, right? I'm doing an experiment. I put stuff in a cup. You figure all that out. I gave you data. If there are spatial correlations in my system, you have to tell me. Yes? Sediment. Okay. Yes. So the point is that is this a buoyancy neutral system, or am I imaging in a plane and things might be settling as a function of time? Again, I don't know. You have a movie. See if they leave the frame of reference in a way that you can't understand it. Then you tell me there is gravity. Yes. Boundary conditions. Yes. I should probably tell you the boundary conditions, but the experimentalists never do. Because they don't know what the boundary conditions are either. You have to subsample your data cleverly so that the boundary conditions don't matter. Other comments? Okay, this is all things I will tell you. Now you tell me what you will measure. What can you extract from a movie? Okay, that was exciting, but I was not able to resolve the conversation. So let's go this way. What was the statement here? Positions. Okay, so what you will generate is a data set of x1 through xn, from frame 1 through frame n. Right? Okay. Orientation. Okay. Orientation, how am I defining orientation? Am I able to resolve the orientation in one frame, or am I using two frames to figure out what the orientation is? One frame. So I have an elongated object that I'm able to resolve. That may or may not be true in the data. I might tell you that you have an elongated object, but you might never be able to figure out which direction it's pointing in by looking at one frame. You have to look at subsequent frames and see what's happening to figure out which direction it's pointing. But yes, orientation. So I get some in the same spreadsheet. I add theta 1, theta n. What else? Okay, so that's the raw data. What can I compute from here? Velocities. So I take this guy, this column, and do differentiation to produce the velocity column. So the velocity column is a derived quantity. The reason the measured quantities will have systematic noise associated with your measurement, your derived quantities will have additional numerical noise, right? So you want to make your derived quantity sit in a separate column in your analysis. So you can go back and ask, did I screw something up? Do I have to change my noise tolerance? Does this make sense? So velocity is a derived quantity. Whenever somebody gives you a movie, you are calculating the velocity. Does that make sense? So it depends on your computational technique. Of course not. If you take one derivative, the data might be so noisy that you get crap. Absolutely. But let's assume I'm a good experimentalist and I gave you data that I can tolerate 2 to 3 time derivatives without degenerating into garbage. Angular velocity. How do I define that? So it's like theta dot. Okay. So I take theta dot and I construct angular velocity. Okay. Yeah, okay. Density. Those are coarse-grained variables. What else? Yes, so what correlation should I calculate? Pardon me? I should calculate theta of t prime. Theta x of t prime. Is that what you're thinking? And what do I mean by calculating this? Because usually when I'm a theorist, I write this. What am I doing when I'm taking this from data? I mean, translate this into a calculation I can put in my Excel spreadsheet. This is my Excel spreadsheet. What do I do to do this? I mean, is it obvious? Does everybody know that you are supposed to fix one time, then look at the distance away from that time, then change that time to build the ensemble? Does everybody know what I'm talking about? That's what I mean by saying, what should I write here? Because all of these things should be made explicit as to what it is that you did. We don't have room to do any of this in our papers, right? And we write papers, but it's you guys who have to figure out what that paper means. So it's explicitly writing it down will help you. So what I mean is that if you want to do t and 0, t and t prime, t plus delta t, I fix t to be some time, right? Sum over n equal to 1 to capital N, theta of t, tm plus 1 plus delta. Right? I sum over all of the possible m's that I can get. Is that right? And then I divide by the total number that I have. You're saying spatial correlation functions in the density or spatial correlation functions in what are you saying? In the orientation. So I want to define a polarization field. Is that what you're saying? I define a polarization field and I use this field. So then there's a coarse graining window. How do I coarse grain my data? What is coarse graining? How do I get to this guy and this guy from my data? Okay. So these are the kind of things that I just wanted you to think about for a moment. Now you're done having fun. Switch to the second exercise. The second exercise is all math. The second exercise, basically what I want you to do is read the first part of the problem carefully. Solve part B. Don't spend your time solving part A right now. Solve part B. Oh, sorry. Because I want to use the solution of part B tomorrow. So you want to solve part B. Everything else you can do in the tutorial. I'm happy to help you and I will also post solutions. Did this diffuse everywhere, the problem? Just the one? Pardon me? Yes, thank you. Yeah. Here you go. Anybody else? Go ahead and ask me questions if the top part, all of the English before the math starts, is unclear. May I ask everybody to look up for a moment? Is this okay? And just for the statement about all other higher cumulants being 0, that goes back to eta being a Gaussian process. Right? A Gaussian process only has 2 cumulants. And the converse is also true. It's called Parseval's theorem. If you find any probability distribution that only has 2 cumulants, it has to be a Gaussian. So you can use that in your data by using cumulants to figure out whether your data makes sense or not. But is this okay with respect to up to the cumulants of delta theta equal to? Okay. Now, I'm going to let you do the power series expansion on your own. This piece of information, the solution for part B, I will assume you know how to do it when we solve for self-propelled particles and stuff tomorrow. Okay? So for the moment, put away the in-class exercise. We'll continue this problem in the tutorial section if you want to talk about it. But for now, come back to me. Let me talk at you for a few more minutes, and then we'll stop. Okay? Okay. Now, if I write this and say this is the diffusion equation, everybody has seen it, right? Okay. What I want to do for the 10 minutes or so that we have left is I want to tell you how to derive the diffusion equation from the Langevin equation. It's going to be painful. If you thought it was painful so far, you've not seen anything. It's going to be painful now. Okay? But if you bear with me for 10 minutes, you would have seen a whirlwind of stochastic calculus and non-equilibrium statistical mechanics, which usually takes a long time to build. Okay. Let's start with some definitions. What is this concentration field? I don't know. So let me start with the microdynamics. I assume that my system undergoes a microdynamics given by an equation of this form. What does the notation mean? That bold A stands in for a vector of some m variables. Okay? And V of A is some deterministic interaction, and F of T is some stochastic interaction. Just as an example for a vector like this A, if I had one particle in 3 dimensions, what would be the dimensionality of capital M? I have one particle in 3 dimensions, right? What is capital M? I'm sorry, I should have cleaned the board while I was harassing you guys. So I said that A, the bold font A, is some A1 through AM, right? I'm asking for one particle in 3D. What is M? I heard a number. 6, yes. Is that okay? Does everybody agree with the 6? 3 positions, 3 velocities. So I'm just using this vector notation as a placeholder that hides all my dimensionality, number of particles, drama like that. Okay. So I have some vector, and the stochastic force, I take it to be of this form. The force is a vector, and I'm not necessarily assuming that the forces in different directions are uncorrelated. There could be some tensor coefficient sitting there that tells me about correlations in different directions. For example, when you come back and do the ellipse problem that you guys were looking at a moment ago, this is the nature of the stochastic force there. Okay? So this is my microdynamics. This is what I'm going to use in place of the microdynamics for one particle in one dimension we were using to do the math up to this point. Okay? Any problem with the notation? Okay. Let's assume this is okay. And let me define one more quantity, this guy f hat, which I'm going to call the probability distribution function. For the purposes of defining this probability distribution function, I have exactly one trajectory. I have one realization of the stochastic force as a function of time from when I started the experiment to when my experiment ended. I hold that fixed and ask what is the probability of these other variables doing something. Okay? And this is a probability distribution function, so it's normalized. If I integrate over all possible values the A could take, this should add up to 1. Yes? This implies that this has to be the dynamics of F hat. This is just a claim at this point. You have to tell me if you're happy with this claim, or should we talk about where this claim comes from. I have a conserved quantity. I'm taking a derivative of that conserved quantity with respect to time. You should flash back to E&M and things like that and think about Gauss's law and Stokes' theorem and things like that to realize that the dynamics of a conserved quantity will always be of the form that I'm suggesting here. The integral over the whole system of F has to be 1. So if F decreases here, it has to increase somewhere else. So I can draw a circle around the region where F is decreasing and figure out what the change in F should be. You integrate over the surface, that will give you the derivative, and so on. This is something that you would have done in an electromagnetism course for sure. Right? Use charge conservation to figure out the dou rho by dou t equation. That's all I'm doing here. I'm just stating that F hat is conserved because if I integrate over the whole system, it's always 1. So if it decreases here, it increased outside. So I can figure out how it will increase. Okay. Now, let's do some algebra. That's the equation I'm starting with. I put in the microdynamics into that equation. Is everybody okay with the new equation on the board? All I did was I took my dou A by dou t is equal to V of A plus F and substituted it into this equation. Yes? No? I don't care. I'm hungry already. Okay. Now, I want to formally solve this equation. I'm going to display the solution and let you react. Reaction should be yelling and screaming and dramatic expressions of unhappiness. Okay, let's go back a step. Let's take this equation. When I solve this equation, I realize that this guy is an integrating factor, right? I defined V bar as e to the CT V. Put it in there and write an equation for V bar. Isn't that what you do when you want to solve a first order differential equation of this form? Yes? I'm doing the exact same thing here, but only instead of a constant friction coefficient, I instead have an operator L that's associated with the deterministic part of my motion. Do you see the analogy? I'm just defining an operator L that encompasses the deterministic part of the motion. I'm using that as my integrating factor to formally solve my equation. And why am I calling it a formal solution? Because I didn't solve anything. The thing that I'm solving for is still sitting on the right-hand side of the equation. Do you see that? I'm nominally solving for F hat, but I haven't solved for F hat at all because it's still sitting here. That's why I'm saying I formally solved the equation. I didn't solve it. I just rewrote the equation in a different form. Maybe. right now you can only follow this by analogy because I'm not doing enough math to track through the entire calculation. So you want to analogize to this first order differential equation and see if you can follow along with respect to the calculation I'm describing. Okay. Now, here is the claim, second claim. The first equation together with the second equation implies the third equation. Stare at the third equation, compare it to the first equation, and see if you can figure out what I did. And this should be symbolic manipulation. You should turn off your physics brain, you should turn off your intelligent brain, and just look at the symbols. Which symbol moved where? That's the best way to do algebra. It's symbolic manipulation. Turn off your brain as much as possible. Look at the symbols, where did they move? What I did was I took the second equation and substituted it into the second term of the first equation. Yes, ma'am. Which exponential? Or the first term, you mean? I probably am stupid because I wanted the equation to fit on the slide, so I probably dropped that. Yes, I lied. I have dropped the initial condition part of the problem. Because the initial condition doesn't matter, and my equation didn't fit on the slide, so I dropped it. Yes, you should keep that also. That will be one more term. Do you see what I did? Apart from the mistake that was just pointed out, what I did was I took the second equation and substituted it into the second term of the first equation to construct a new version. This is all just rewriting the first equation in lots of different ways. I haven't solved anything. But this rewriting of the equations in several different ways is a useful technique when you're trying to figure out how do I extract from this something I can calculate. You just keep moving the symbols around so that they start suggesting some way to do the calculation. So I get there. Now, let's examine what happens to this equation when I noise average it. So I'm going to define a new distribution function f, which is the noise average probability distribution function, which is the old probability distribution function, but now I'm going to average over all possible realizations f. When I wrote down the little f hat the first time, I had fixed the stochastic trajectory, right? Now I want to allow all possible stochastic trajectories, so I want to do that angle bracket average that we have been doing so far. Okay. Now let's just look at it. The first term is just going to become little f, right? There isn't anything else there. Little f depends on, little f hat depends on capital F, and when I average over it, that by definition is little f, right? So that's just definition. Same thing in the second term, just definition. Third term, what should happen to the third term when I average it over noise? It's a Gaussian white noise process that has zero mean. So this term will be 0. Yes? Can everybody see that this term will be 0? Because it has one eta in it. The capital F is the eta. Then I look at the last term. Now there's something interesting here. There are f's all over the place. There is one f here. There's another f here. And then there is an implicit f inside the f hat. So what I need to average, going back to our notation before this horror descended on you, what I want to average is I want to average over noise some eta of t, some eta of t prime, and some other function of eta that I don't actually know. Yeah? Okay. If this was 0, then there would be no Fokker-Planck equation and all of us can retire and live on a beach. But it turns out that if I'm going to claim without proof, because I don't want to build the Ito calculus we need to get here, claim without proof that if you calculate this average, because you have two f's and an f hat, what you end up getting is a little f and the noise strength. I'm claiming without proof. But let me give you a cartoon way of thinking about what is happening here. So let's examine this case. I want to calculate this noise average, right? if you were doing something naive, which is what we usually do when we are doing a StatMech class or a thermo class, because class needs to be pleasant and you don't want to do any unpleasant things, you would say, oh, I will say this is approximately equal to just this correlation times this correlation. Don't you do that all the time? You get up some 2-point correlation function you can't calculate and you say it's a product of the 1 point. Supposing I did this, what I would get is 2b delta of t minus t prime f hat of a eta. I mean f of a. Yes? If I compare what I did here to what my claim is, you will notice that the only difference is this factor of 2. This factor of 2 gets resolved when you do the Ito calculus properly. And I'm not going to tell you how that works. This is what Rodrigo was hinting at this morning, namely that when you're doing stochastic calculus, you need to decide whether you're multiplying the prefactor at the initial time, you're multiplying the prefactor at the late time, or in the middle time. For this particular process, it doesn't matter which time you pick, you get the same answer. But you have to do that exercise to be able to figure out where the half went, where the 2 went. OK, so I'm going to claim without proof that that happens. And supposing that happens, then what I get is the world-famous Fokker-Planck equation. This is the most generic version of a Fokker-Planck equation. I'm not saying anything about non-interacting. I'm not saying anything about anything, because that V could be any arbitrary interaction between these degrees of freedom, right? This is a Fokker-Planck equation. And the Fokker-Planck equation is a very, very beautiful equation. It has a non-adjoint operator, all kinds of exotic properties to it. And of course, there are big fat books written about this equation, right? For the particular case that we were thinking about before, one particle in one dimension, the Fokker-Planck equation becomes this guy at the bottom. By the way, all of this stuff is written out along with the English that is coming out of my mouth in the lecture notes that are either already posted or will be soon posted on the website. Okay? I'll also outline what else is in the, oh, I'm out of time. Okay. I'll stop in 1 minute. Yeah, okay, so that's my Fokker-Planck equation. This is the special case. You can get to the special case by just making the mapping that A is now just X and V. The capital V is just V and minus C over mv, and F is 0 and noise on the velocity and so on. So if you take this mapping, you'll end up with the Fokker-Planck equation that applies for our case. We'll be working with the version of this Fokker-Planck equation tomorrow. And oh, I said I will stop talking and I have more slides now. I will stop talking. This is fine. So now what's going to happen is we're going to pick up from here next class, which is again before the tutorial. So I'd like you to look at part B of the problem that was handed out so you're familiar with it when we launch into self-propelled particles. Okay, because we'll build on this to get to some of the things that we need for self-propelled particles. Also, what else is there in the lecture notes that I've posted that I'm not going to have time to talk about during the lecture is how these fluctuation dissipation ideas and these kinds of non-equilibrium StatMech ideas belong for Hamiltonian systems. Because classical mechanics is a Hamiltonian system. Because we are all doing active matter and whatever cool things, we never meet a Hamiltonian in our life. But all of these things come about for Hamiltonian systems, and some of this information is there in your lecture notes. And I'm happy to discuss it with you either during the tutorial or during lunch or something like that. Okay? All right, we'll stop here. I apologize for going over. Until tomorrow.
Okay, thank you very much, Aparna. I think we made most of the questions during the class, but if anyone has a question.
All right.
Okay, so maybe we can leave to the coffee break and to later.